All right, today we're going to be talking about friction, and this is like take 3 because my microphone keeps picking up the wrong thing. Drives me nuts. Okay, but don't worry, we can do this. We'll stay focused. It's as if there's some sort of friction that's working against us. See what I did there? I tried to blend it in. So yes, today's topic is friction. So let's talk about the graph that we should be seeing here. All right, so we want to make sure that we're talking about the right thing. So if we look at friction, then it should look like this. All right, so here's my graph, and we're going to draw some stuff. So when we did the experiment, it'd be like force of friction, and then this would be time. So in the experiment, you had to drag an object, and you saw or are going to see, depending on when you do this, you are going to see a very interesting graph, and it's going to go up, and then it's going to dip down. I'm color coding this for your convenience, and then it's going to be all sorts of jagged. Okay? Now, this is interesting because it means that friction is not a single value. Friction actually changes. Okay? And there's two major segments that we need to talk about. This first segment in blue, so I'm going to color code it, is when we have no motion. All right, this is where you are going to be pulling on an object, or in real life, it could be like you're pushing, and it's just not going anywhere, you're pushing harder. And because it's no motion, we refer to this as static. All right, so this is static friction you're experiencing. And as you see, it is a reactive force. It gets higher and higher and higher as needed. But eventually, it reaches a max static. And once you reach that max static, it's like standing on a table and you're jumping on the table, you add more weight to the table, all these things, and you're like, oh man, the table's indestructible. And then you add one more thing to it, and the table's like, yeah, no, I'm broken. Okay. So this is the maximum force that friction can oppose. Now, why does this happen? All right, so now I'm going to do my best to make some drawings over here. So let's say we have a zoom in on an object. All right. Every object that you think is smooth is not smooth. All right, even if you think it's the smoothest thing in the world, if you put it under a microscope, it is extremely rough. It is full of all sorts of peaks and valleys. So when two surfaces come in contact, we've got like surface one here in green, and then here's the other surface. So I'm going to just kind of try and marry them up to a point so that we got something here. All right. So you'll notice they're not like perfectly in line because they're randomized. But you see that they kind of will settle into these peaks and valleys as best they can. And once they've settled in there, you actually have these opportunities like here and here, and I got one coming up about here and all these stuff, to actually have sideways interactions. And so you basically get these normal forces. All right. Where the two objects are actually going to fall into each other's peaks and valleys, and then they're going to actually push sideways on each other. And just like any normal force, you can push and you can push and you can push, but eventually you're going to be able to overcome that normal force. And once you do, these two surfaces, instead of falling into these peaks and valleys, they are going to, let's see if I'm going to attempt to try and reproduce this. I promise nothing. All right. So they're actually, instead of falling into each other's peaks and valleys, they are now going to kind of skim across the surfaces of each other. All right. And so they're going to ride across the surfaces. And so we don't have any opportunities for these little normal forces, these micro normal forces. It's not like they're huge or anything. But we don't have any chance for this sideways pushing. Instead, it's skipping across the surface. And so now that skipping across the surface, we are in this red region over here where we have motion. And in physics, we refer to motion as kinetic. All right, kinetic means motion. Kinesiology is the study of the human motion. We had kinematic equations. Those are the equations of motion. So kinematics kinetic means motion. okay? And so here you can see that we kind of are bouncing around and we kind of have an average value here because it's skipping along. It's like you riding your bike along a dirt trail that's not exactly the evenest thing. And you're kind of holding on, you're going, you got that going. Whereas if you were to go on something totally smooth, like brand new asphalt, you would not have that problem. Okay, but if you're skipping along an uneven surface, you're going to feel those vibrations, and that's why the frictional force is not a constant value when you are in motion. The kinetic frictional force is not going to be uniform, but it's going to kind of bounce around a certain region. And so that average of those bouncing, that's what we kind of use for our kinetic friction values. So this is what really causes friction, this interaction of the peaks and valleys of the two different objects. So again, up here, this would be our static segment, and this would be our kinetic, E-T-I-C, kinetic. So again, static, those peaks and valleys fall into each other, so it's hard to push and get to move. But once you do push hard enough, they'll pop out of those grooves and then skip across the surface. And that's where you get your kinetic. Pardon me, I had the hiccups. Now, you'll notice that there's a great difference here between the max force of static friction and then the average force of kinetic friction. This harkens back to the days of yore, which was like, oh, forever ago when I used to play football as a kid when I was your age, which, yes, the moon was like a different shape. Okay, it was a while ago. And so I was a football player. We had to push the sled, and you'd have to push it a certain distance. And so they would, the guys on the team was like, just don't stop pushing, just keep pushing, keep pushing, keep pushing, keep pushing, because the sled start at rest. And so you had to hit it with like all your might, and eventually you get to move. And once you got to move, then you went from this high value here of static friction, and all of a sudden, once it got moving, you had to actually apply a smaller force. So it was easier to keep it going because now instead of being stuck in those grooves, it is skipping along the top of those grooves. Now, of course, the moment you stopped because you're exhausted, well, it goes back up to here again, and then the next group of kids would have to take their turn, and they'd have to smash it and crush it from here and try and get to move so that they could decrease the force. So that's why, there is a statement where it's like, hey, something in motion, it's easier to keep it in motion than to get it in motion. That's just a true physics concept across many different areas. All right, so that's the main thing I wanted to talk about. Now, a few sidebars here, okay? One thing to talk about is that surface area does not, oh, he did capital, affect friction. I hope I put the right effect there. Is it an A or an E? I always have a hard time with that. I guess that's why I became a scientist instead of an English major. So surface area does not affect friction. And the reason why people think it does is because they get force and pressure confused. They think that they're the same thing, when in reality, pressure is force per unit area. So if you change the surface area, then you're going to change the amount of pressure that you're applying to an object. And this really only takes into account when you have like, hey, well, what if I change the surface area of the object and I'm displacing more force? You're like, well, I'm taking the same force over a greater area, so I'm not going to fall into the ice, that type of thing. But friction's like, dude, look, these ridges, they're all over the place. So if you want to spread them out, that's fine. You're going to run into just as many ridges. Like, it's not going to be a factor. Okay, so there will be this balance between pressure and force, and it'll all work its way out in the math. So I don't really want to go into that, but I just want to make the point that surface area will not affect the force of friction. The only thing that are going to affect the force of friction are the surfaces that are interacting and how hard they're pushed together. And that's why we walk away with our equation of friction equals mu Fn. Now again, that's our main equation, but I do want to emphasize a few elements. Like one, let's clean up our workspace here. We got these dots showing up, drive me nuts. All right. I just want to bring up that this mu value here, right here, this is our coefficient of friction. And we are going to have two mu's, so we're going to have a mu sub s if it's static and a mu sub k if it's kinetic and it's moving. I need to be disturbingly clear about this. This is not the letter m. This is the letter mu, okay? mu. It's a Greek letter, okay? I would be happier if you wrote the letter U than the letter M, because M is mass. We don't want to get that confused. So let me just do a real quick, how do you draw the letter mu? Okay, so we do a line. This is how I learned how to write when I was in grade school type of thing. And so you start below the line, up to the middle line, and then you draw a lowercase u. Yay. All right, so that is a mu. Honestly, it's not my best mu, but I'll take it. Okay, it's not the letter M. So I think this is pretty much all you need to know about friction. This is the vast majority of it. And yeah, let's do some math, do some practice. And as always, let's enjoy science and play some video games or board games or, enjoy life too. Thanks for watching, and I will be around, well, more.